have the guest Alex Merced. Alex is a developer advocate for Dremio with a history of creating content to enable developers of all types through his personal projects like devnursery.com, the Web Dev 101 podcast, and the Data Nation podcast. Alex has been a developer with companies like Crossfield Digital, Campus Guard, Gened Systems, and others, along with being an instructor for General Assembly boot camps. And he is also a Florida native, so he has that going for him as well. Um, Once again, thank you so much and welcome to the Tampa Bay Data Engineering Group. And today we'll be talking about Iceberg. So, Alex, please take it away.
Hey everybody, my name is Alex Merced. I'm a developer advocate with Dremio, and I'm going to share my screen so we can see the presentation. So here we go. Let me get that all set up and share and hit slideshow, and we begin. So today we're going to be talking about Apache Iceberg. Specifically, we're talking about the architecture of Apache Iceberg to kind of learn like not only what it is but how it works, what makes it so special. So again, my name is Alex Merced. I do recommend to follow me on Twitter. I'm constantly putting out content on table formats, comparing the different table formats like Iceberg, Hoodie, and Delta Lake. And I oftentimes am posting that content over there on Twitter at AM Data Lakehouse. AM Data Lakehouse. But yeah, we'll continue on. So over this presentation, we'll be talking about what is a table format. Because to talk about like why Iceberg is such a special table format, we need to know what a table format is. Why do we need a new one? What's wrong with the solutions that we've had in the past? And then the architecture of Iceberg. Like, okay, so it's this cool solution that's solving a lot of these problems that we used to have, but how does it do that? Like, what about the way it's structured, about the way it organizes data that makes it special? What happens under the covers when you create a table, when you do a read on the table, insert into a table, when you do create, read, update, and deletes. And when it all is said and done, not only do we now know how it works, but what are the benefits? Like, what does this bring to the table? What are these extra features and innovations that I have? What's the benefit to me at the end of the day? So that'll be what we'll be covering. So first step, what is a table format? Bottom line is this. Imagine you have your data lake. So basically, either it could be like, a Hadoop cluster somewhere with thousands of files. It could be data on S3 or Azure or Google Cloud object storage. But the idea is you have all these files that you've ingested from all sorts of different places sitting there. And you want to run analytics on that data. The problem is like, even though you may have one data set stretched up across, 1,000 or 10,000 Parquet files, how does your software know? Like, how does your analytics scripts know these 1,000 files are treated as one table, as one data set? Okay, we take this for granted when we're using databases and data warehouses because all that stuff happens under the hood. I just know when I'm using Postgres or X data warehouse that I can just put data in. It's a table now, and I can run queries on it. So what happened is originally you had like with Hadoop you had like MapReduce, and you would have to like write these JavaScripts to say, hey, these files are my data set and I'm running these operations on them. And then came along Hive, and Hive tried to make this a lot simpler by saying, you know what, instead of having to write these like long JavaScripts, what if you could just write SQL? And that SQL would automatically turn into these MapReduce scripts and just make using MapReduce a lot easier. Okay, going back in time a little bit, but this is kind of like how things got started. But to be able to run SQL statements, to be able to run analytics, you had to know what the table is. So we had to kind of come up with a way to define that table in the file system and say, okay, these files are the table. So what Hive did, and again, at this point, you're working primarily with the Hadoop file system. So certain considerations aren't quite there yet. What it does is they take the approach of using a directory approach. So they said, okay, all the files in a particular folder are a table, and then all the subfolders are the partitions, and then that's pretty much how this would work. And that works. That's simple enough. Now whatever engine is running the query can sit there and say, hey, if the file is in this folder, it is part of the data set. And that worked. That allowed people to be able to run SQL statements, be able to like treat certain data sets as consistently defined data sets across different analytics platforms. It made life easier. And over time, that became the standard. Everyone was using Hive when they were running analytics on their data lake. And that's a big benefit because when you're like the standard, that means all tools are going to, support you. So pretty much any engine you can think of supports Hive. Also, it basically made it where you can organize your data in ways that you could run faster queries because you could do things like partitioning um, that allow you to sit there and basically chop up your table into subdivisions and basically only scan the subdivisions you need whenever you run a particular query. It was file format agnostic. Inside that folder could be different types of files, and they would all be treated as one data set. Basically, you could atomically update a whole partition, because basically if you were to update something, it would update that partition, which is a good thing when you're updating a huge amount of that partition. As you'll see in a second, cannot be so good when you only want to update like a few records in that partition. And again, it allowed us to provide us with a single answer to like, what is a table? Okay, so now no matter which team is running analytics, that table is always going to have the same definition. And there's definitely a lot to be said about that, so that we don't have different teams running, analytics on a different subset of files because everyone, selected the different files to be that data set. Now the cons were smaller updates were really difficult. What if you only wanted to update one record? Well, what would happen is that it would still update the entire partition. So you're updating the entire partition for like the update of one record, because it still has to kind of go through the partition to go find that record to update. So that, well, time consuming, not the most efficient thing. If you wanted to update multiple partitions, there really wasn't a way to do that safely. So if you had like multiple writers, that could be an issue. Okay. In practice, multiple jobs modifying the same data set, even if they're in the same partition, would be hard to do safely. Okay. So basically you had all these like sort of like logistics where it's really hard to kind of have concurrency, whether it's multiple readers, multiple writers, and avoid doing that all in a secure sort of consistent way. And the thing is that since everything was so built on this whole idea of files, what would happen is that, if I'm like the engine who's scanning the files, I would first have to like, open up the folder. Then in the folder, I'd see all the like different directories for the partitions. I'd open up a directory with a partition. Then I have to like go through, scan each file. And that would take a long time because even if you only scan a partition's worth of files, you still have to scan every file in that partition. And it would take a lot of time to sit there and like open the file, read the file, close the file, open the file, read the file, close the file. These kind of operations extended the life of the query, made things take longer. Okay, especially when you're talking about like petabytes and petabyte scale of data. And especially when you're taking a look at features like partitioning necessarily wasn't always very intuitive for the consumer. An example would be like this. So imagine that you have a data set, we'll say like sales, like it's the sales for the last quarter. And there's a timestamp field that says, okay, here's the timestamp of when the sales occurred. But you want to partition the data by like year and month, or let's say just by month. Well, the problem is the timestamp doesn't necessarily isn't enough. What you need to do is create a separate field that's like a month field, like there's like 0 through 11 for the 12 months. So you generally have to run some sort of like, first you'd have to create that column and create that data set. So you have to create this whole column just so you can partition, and then you'd have to partition it by that column. Now what's going to happen is that your data consumer isn't going to intuitively think, oh, there must be a month column. They're going to think, I want to query like any sale that occurred between this timestamp and this timestamp. But if they don't add an additional filter for that month column and say, hey, can you get me like everything that was inside month 5? Then what's going to happen is that they're going to end up doing a full table scan. So you'd end up having these accidental full table scans and all this additional work of having to make sure that your data consumers were aware of how the table is partitioned, because they need to know to add those extra filters to take advantage of the partitioning. So that's not very convenient. That's something we could probably make better. Also, like the Hive table statistics were often stale because what you would have to do is like periodically to get table stats, you'd have to run these analyze queries, which would one take a long time because you're scanning the whole table to generate these stats, and basically your stats basically were only as up to date as the last time you ran that query. So we want to improve upon that. So we had all these sort of problems initially with that sort of Hive format and using that Hive format. So then what happens is that over there at Netflix, they start asking themselves like, yeah, these issues, these are a problem. We want to work on that. So they had a set of goals. They kind of wanted to make sure that the table's correctness and consistency. So again, that the table is consistently defined no matter what tool they're using, and that it's correct whenever anyone's querying the data. We want faster query planning and execution, and generally both they go together, because if you can plan a better plan leads to a faster query because you're scanning less data, and generally if you have an efficient metadata, you can then plan that query pretty quickly and effectively. So we basically want that. We want to allow users not to have to worry about the physical layout of the data. So we don't want them to have to worry about like how the files and folders are organized. We don't want them to have to worry about how it's partitioned. They should be able to just query the data in the intuitive way. So in that case, just query that timestamp field, and they would automatically benefit from any partitioning that's being done. Like, they should just focus on the analytics. They shouldn't have to be like having to also know all the stuff about just sort of the engineering of the table. The table should be flexible. Like, I should be able to update the schema. I should be able to update how the table is partitioned. I should be able to update how the table is sorted. All these different things when I need to. Because traditionally what would happen is that if I wanted to change the schema, well, I'd have to rewrite the table. So do another like CTAS statement, recreate the table with the additional column. And then I have to write all those petabytes of data over again. Or if I wanted to change the partitioning, I would have to rewrite the table. And those are really expensive operations. So we want to kind of avoid all these things and be able to do all of these things at scale, at petabyte scale. So the solution they came up with was Iceberg, which took a different approach. And this is sort of like where Iceberg is extra unique relative to like other formats like Hoodie and Delta Lake, because they both took at the core of Hoodie and Delta Lake, you still like adopt that sort of like file system that Hive had, where you basically you have the folders and the subfolders. Iceberg focuses on looking at everything as a list of files. So essentially, at the end of the day, like what matters is that the files that make up the metadata list the individual files that are in the particular partitions and whatnot, which is going to give it some flexibility on how it organizes the files. Like the files don't have to be in that Hive style folder format. They generally are by default because why not? But they don't have to be, which is going to allow you to be able to do better at scale on object storage. It's going to also allow you to just add files to your table that might be just in other locations, which is really cool. Now, what Iceberg is and isn't, okay? And generally, what Iceberg is a specification. So what Iceberg does is they have a standard way that the metadata is structured and written, and basically by having this sort of standard, this sort of agreed upon contract of how the data should be structured when we store this metadata, it allows any engine that exists the ability to create the functionality to read, write to those tables. Okay, and what they do to support that is they do have a set of APIs and libraries to help operate on and run utilities on those Iceberg tables. But at the end of the day, like things like performance and things like that are going to be very engine specific. So basically, like how Dremio reads an Iceberg table is going to be different than how Trino reads an Iceberg table. It's going to be different than how Spark reads an Iceberg table, and because it's up to each of those engines to implement that specification. So Iceberg is not a storage engine. It's not responsible for storing the files. It's not a file system. So you still need to have somewhere to store the actual files, which could be HDFS, could be object storage, your choice. It's not an execution engine. So again, you'd still need a tool like a Dremio, like a Spark, to actually run the queries on the data. And then each of them will, how they actually do it, how they actually plan the query, how they take advantage of that specification can differ. It's not a service. Okay, so it's not some sort of ongoing process that you're running. So you don't have to have like an Iceberg server somewhere to maintain your Iceberg tables. It's just essentially the metadata will be stored in your file system, your S3, your HDFS, and it's just going to have certain data that an engine that goes then scans those files can then plan a query effectively. So, but again, there's also like a Python library, a Java library to run basic utilities on those tables, so you can do basic like maintenance and things like that. Okay, so let's take a look at how Iceberg is structured. So essentially, like this image here is essential like structure of like how Iceberg works. And there's essentially like 5 components. So you have your catalog, your metadata file, your manifest list, your manifest file, and your data file. Okay. So first we start out with the catalog. The way to think of the catalog is I like to think of it as a phone book. Okay. I mean, I'm sure there's more like current analogies, but I think the yellow pages puts a picture in the mind. Well, so what would happen? So back in like the 90s and beforehand, what would happen is that if I need to know where like what Bob's phone number was, I would go grab the phone book. I would like flip through the pages and look at Bob, and I'd find Bob's phone number. Okay, that's essentially what the catalog's role here in the iceberg table is. Like all I really want to know, all the engine needs is to know where the metadata is. Okay, all the juice is in the metadata files that are just written to your file storage. But we want to make sure that we're always pointing to the right one. So generally we're going to have some sort of thing like a JDBC, any database that supports JDBC, like a Postgres, could be HDFS, could be a Hive metastore. There's actually a special one called Nessie that's really cool, built particularly for Iceberg, that actually like gives you Git-like features with your Iceberg tables, where you can do like branching and merging. That's called Project Nessie. You could also use AWS Glue, but some sort of like DynamoDB, some sort of layer. But what it does is you're creating just a atomic pointer to what is the newest metadata file. Okay, so if I want to know, hey, what is the newest metadata file for table 1? So I'm the engine. I'm like, okay, you told me to go do an operation on table 1. Where is table 1? First thing the engine's going to do is going to go to whatever catalog that is, whether it's Hive, whether it's AWS Glue, whether it's Nessie, whatever you're using as a catalog. Okay, and again, every company can then choose what they want to use as their catalog depending on their needs. That's going to be where the engine goes to see, okay, hey, where does this table exist? So that's what the catalog does. It's literally just saying, hey, here's where that file you're looking for is. Okay, so that's always going to be stop number 1. Okay, and it's going to get that current metadata pointer for that table. Like, where is the newest metadata for that table? But then that takes us to the metadata file. So this is actually, again, just a file just written wherever your files are written. And this file, think of it as like a global table-wide file. Like this defines the table as a whole. So it tells you, hey, what is the current partitioning scheme? Like, how is this table currently being partitioned? How was it partitioned in the past? What is the current schema? How was the schema in the past? What is the current snapshot? What were the previous snapshots? So all the data you'd want to know about the table at the highest level is going to be in this metadata file. Okay, so basically, again, think of it as like the global, like, what is the table file? But at some point, I'm scanning not the table at all times. I'm scanning the table at one particular point in time, one particular snapshot. So what's going to happen is that when they scan that metadata file, I'm going to look for that current snapshot if I'm the engine. I'm looking for that current snapshot, and that's going to tell me which file that current snapshot is. Okay, and that file is called a manifest list. So I'm the engine. Again, you told me to scan table 1. I went to the catalog, found out where the new metadata file is for table 1. I scanned the metadata file, found out what the current snapshot is, and now I know where the file for that snapshot is. And I'm going to go to scan that file, the manifest list. Now, a lot of people would expect that the next step would just be to list the files that exist in this particular snapshot. But what Iceberg does is adds this extra layer, which is going to allow for even faster planning. So instead of having a list of files, we're going to have a list of groups of files. So what's going to happen is that the actual list of files are written into these manifests. And generally, like, there might be one or more manifests per partition. So basically, if I'm partitioned by month, each month would have like a folder with each of these, or we'll have a manifest or more, depending on how many files there are, for that partition. So what's going to happen is that as the engine, what I can do is that these manifest lists list all the individual manifests that belong to the snapshot. So the manifest list is the snapshot level metadata file. It defines a snapshot, a point in time. But the engine, what it can do is it can check, hey, what partition does this file cover? And if it doesn't fall into like the bounds of this particular query, I can just drop that entire manifest. So instead of having to drop each file individually, I'm dropping a whole clump of files and saying, hey, I don't need to scan these. And I can even not only, it also has like the upper and lower bounds of the data in that manifest. So even for those that are in the right partition, I can say, hey, do they have any values that would be within my query's filters? And then still drop that manifest. So I can drop whole chunks of files, which is a lot faster than dropping individual files. So I can do this big sort of larger filter on the files I'm going to scan at this point. So once I've done that, I've dropped all the manifests that I don't plan on scanning. I take the remaining manifests that I will scan, and I'll start scanning those. And these manifest files, they list the actual individual files. So each manifest list will have one or more files that contain actual data, and they're listed. And then what I'm going to do here at the manifest level, I can go to look at metadata for each individual file. In the same way that the manifest list had like the upper and lower bounds of certain data in the individual manifest, the manifest has the individual upper and lower bounds, like what is the maximum for this field, what is the minimum for this field for each column for the data files. So now I can take a look at all my filters and say, okay, hey, is this data file based on the upper and lower bounds really going to have anything that matches my query? Nope, based on these upper and lower bounds, they don't, so let's not even scan that file. So basically, using what's called min-max filtering, you've now reduced the number of files you're going to scan even more. So through the partitioning, I've reduced a bunch of files. Using min-max filtering, I've reduced even more files. So the actual number of files I'm going to have to scan is going to be really, really small as possible. And that's what's going to make the actual scan, the actual query, much, much, much faster. Okay, and we'll show you an example from Netflix, like how much the speed improved from Hive for Netflix. So again, basically, that's always going to be the path. It'll always be, where does the table exist? Let me get the data for the table as a whole, find out what the new snapshot is. Okay, let me take a look at the groups of files in that snapshot, see which of them I need. Now let me take a look at those individual files, see which ones I need to scan. And then once I have my final list, I go scan the files, run the query. Okay. So now that we kind of see the architecture, see like the sort of the general sort of thought process behind these different metadata files, let's actually like do some queries and kind of see what would happen when you run those queries. So first thing we're going to do is we're going to create a table. So here it says create table, table 1, and here basically with like order ID field, customer ID field, order amount field. And again, this is assuming you're doing this in Spark. So again, like the actual SQL syntax can vary slightly depending on which engine you're using. Not much, but like for example, for Spark, you do have to use this like using Iceberg clause to tell Spark that you are using Iceberg when you have the Iceberg libraries loaded up. But you create a table using Iceberg, and then partition by. And let me talk about this for a second because this is really cool. Iceberg has really interesting partitioning features. So remember how we would have to like create a separate column for like a month or a year when I was talking about partitioning with Hive? Well, the way Iceberg handles this is that if I want to partition by that timestamp field, but I only wanted to keep track of like the month, the year, whatnot, it has these transform functions. So here's like hour, there's like day, there's month, there's year, there's a whole bunch of them. And they have some non-time functions too, like bucket and truncate. But what it does is that instead of having to create a whole new column, what it does is that it's basically going to track like the transformed value of that column and then use that for partitioning. So essentially, when it's doing all the processing, it'll be like, okay, hey, what is the month that this timestamp represents? And then put it in that right folder without having to create a whole, one, physically more data in those files. And two, when the actual user like queries the data, if they query based on that timestamp field, they benefit the partitioning. Because in the metadata, it says, in the metadata, it says that, hey, this thing is partitioned like this, an hour on order TS. So it knows, hey, when that order TS field is queried or like filtered, go use the partitioning for that table. So basically that analyst doesn't have to worry about how the table is partitioned. They can just query the table, ask the questions they want to ask, and if there's partitioning that will assist the query, it'll just work, making life much, much easier, which is super cool. But basically what happens when we run this query and create a table, essentially there's no data, so there's no data files to write because we just created a table. And if there's no data files to write, then there's no manifest to write because we don't have any groups of files we need to track. And there's no need for a snapshot. So there's no manifest list because there's no manifest to lists. So the only thing that gets created is a metadata file. Again, just that sort of high level definition of a table. And then we just create an entry in the catalog that says, hey, this new table is created. That's the new metadata file. And you can see here, this is generally like the default way it's going to like set up the files in your file system. Will generally have like a default directory, which will generally lay out the files very similar to Hive. That's sort of its default behavior. But you can see here like table, and then there's like a metadata folder and a data folder. So now let's actually insert some data into the table. So we insert some values. Wonderful. So what's going to happen is that it's going to go through the same process again. So it'll read the metadata file. So it's going to first read the old one to kind of get an idea what the schema of the table is. And then based on the information in that metadata file, it's going to begin writing the data files, like based on the details of the table. So they'll be separated out by partition, sorted by if there's any sort order assigned, all that kind of stuff. Once the data files are written, then we're going to start, it'll then create the manifest files that list all those individual files. And then once all the manifest files are written, it then creates a manifest list that represents that snapshot, and then it creates a new metadata file. And then the newest metadata file will list the previous snapshots and the current snapshot. And then we update the catalog, we update that pointer to point to this metadata file going forward. So that way that becomes the new current state of the table. So nothing is ever getting destroyed. Okay, so by default, no files are ever being modified or destroyed. It's always just new files being written. Okay, we will try to reuse files when possible, which also speeds things up. But the idea is by having this sort of immutable, sort of functional approach, it allows you to save a lot of time and speed things up. Okay. Now, what we're going to do is that we're going to do an upsert. Okay, so basically what happens is we have a staging table with a bunch of data we want to add to our table 1. So again, we have our table 1 staging table, and then we're going to merge them based on where their IDs match. And when they match, okay, they'll update. Okay. And when they don't match, we'll do an insert. Okay. So what's going to happen is that first thing it's going to do, it's going to go back to the catalog, figure out, hey, what's the newest metadata file? Read the newest metadata file so that way it knows what the schema is. And once it knows what the schema is, it's going to begin writing new data files based on the schema, based on the partitioning, based on all that. Then once it's done writing any new data files, okay, and again, it'll only write it on for the new data. So it'll use the old data files for the existing data. It then, rewrites manifests. So any new manifests that need to be created get created. And then a new manifest list for that snapshot that will list any manifests that apply to that snapshot, and then create a new metadata file that covers that snapshot and the previous snapshots. So you can see here, like this is the files you would see in your file system. So you see now there's like 3 metadata files. And you see like the number increments. So like the next time we do an update to the table, it'd be v4.metadata.json, then v5.metadata.json. Okay, and then see like the snapshot files have like snap in front of them, and then these are just your manifests. Okay, and then you can see here in the data files, like the data is again organized in folders by partition. So again, right now still using that Hive style of directory layout, but again, there is a way you can change that, particularly for like object storage. And the reason you'd want to do that, and again, this is a really cool feature of Iceberg, is that on when you're using something like S3, they'll throttle the amount of requests for anything in the same folder or prefix. So basically, by having everything in the same partition in the same folder, you ask for if there's too many files in that same partition, you'll end up having a slowdown of scanning your table. But what Iceberg can do is like there's a little compatibility setting you can turn on, because again, it doesn't matter what the file structure is. What it'll do is it'll take a same partition and chop it up into multiple folders with like unique hashes in their names. So that way you don't have so many files in one folder that you run into this throttling with S3, allowing you to really run Iceberg at scale on object storage, which is a very, very, very attractive feature to a lot of people, because that always sucks when your queries get throttled, right? So yeah, so let's run another query. So now let's actually read the data. Okay, so let's select all data from table 1. So what I'm going to do, I'm going to first go look at the catalog. I'm then going to look for that table's pointer. That's going to point me to the newest metadata file. I didn't specify any particular like time travel or anything like that. So what it's going to do is by default it's always going to scan the newest snapshot, which is snapshot 2 over here. That snapshot 2 points to this manifest list. Then we didn't specify any filters, so it's just going to scan all the manifests. So scan all the manifests associated with that snapshot, and then scan all the data files. And there you go. The query's done. Okay. So that's what's going to happen when it does a select. So it's just running through that pattern. And now let's see one where we actually do specify like a date. So we're going to have some filters on this query. So I'm saying, hey, I want to select anything from table 1 where the date is the following. Okay. Now what's going to happen is that first it's going to go to the catalog, go look for that pointer. And notice there's no more new metadata files. Just to read, you don't generate new files. So reads, no new data has got to get written. So we read the metadata file, we find that new snapshot, we look at the manifest list. But because we have this date query, and again, it's on order TS, so even though we're not specifying like an hour, even though we partitioned it by hour, it knows that it's partitioned by this field. Like, so then what Iceberg is going to do is going to use this information to like narrow down, hey, I don't actually need to query the stuff in this partition because this partition, the 27th, well, you're asking me for the date of the 26th, and this partition covers the date of the 27th, so we don't need that one. Okay, so then it's just going to scan this folder. So it can like refigure out the partitioning, even though you may have partitioned it by hour, you can still get benefits at the month or day level, which is pretty cool because of the way it writes out the partitions and the way like it logically tracks the partitioning. Okay, and I think this is the last one. This one we're going to be using the time travel syntax. Okay, so again, this is specifically the SQL that you would be using in like Spark. Different engines will do time travel slightly differently. But if you do select all from DB table 1 and then you use this as of operator, what I'm saying is say, hey, I want to look at the table as of this timestamp. And what's going to happen is that it's going to do what we've been doing. Go to the catalog, get the metadata pointer, look at the newest metadata file. But now it's going to look at the different snapshots and say, okay, well, let's take a look at the timestamp, which is the newest snapshot that is on or before this timestamp, which is going to be snapshot 1. So instead of going through this path, it's going to go through this path and then scan this manifest list, this snapshot, go through these manifest files, and scan these data files instead. So I can now actually like time travel to historical states of the table because of the structure of the metadata. So just to kind of show you like the impact this can have. So if you're using Hive tables and using Hive, like just to kind of see the benefit. Let's take a look at what happened at Netflix. So Netflix has this Atlas system. So it's just like basically it's this system that collects telemetry data. And basically in 1 month of data generation here on this Atlas system, it would generate 2.7 million files in 2,688 partitions. The problem is that when this was being done with Hive tables is that the query is like you could not like reasonably process more than a few days worth of data at a time. So you couldn't really run like a query on a month's worth of data or a week's worth of data. It just wasn't doable. So what they did is they ran a query, and first they ran the query with a Hive table. And this is still using Parquet filters. Okay, so in the sense that you could still reduce the amount of files you scan by like if you're dealing with Parquet files, you can read those Parquet footers so you can see which like row groups in the Parquet files you need to read. So you can reduce the amount of reading you have to do. But you still got to open the file, read the file, close the file. But it still speeds things up quite a bit. But Hive tables with Parquet filters, it still resulted in 400,000 splits per day. So basically little like unique chunks that would need scanning. That's 400, not total, per day. So for each day's worth of data you were scanning, there was 400,000 splits. And when you basically, just by running an explain query, so basically we're not actually running the query, we're just asking the database to plan the query and tell us how long it's going to take to plan the query. It took 9.6 minutes just to plan that query. Okay, that's with Hive. Now let's see what happens when we switch over to Iceberg. Using an Iceberg table, using just partition data filtering, so none of that min-max filtering I was talking about before. So basically it would just identify like the relevant partitions, drop everything else, and that's it. Just using partition filtering, you went down to 15,218 splits total. Okay, so potential things we might need to scan, 15,218 splits. Okay, and the time it took to figure that out was 10 seconds. So we went from 9.6 minutes just to plan the query to 10 seconds. And 13 minutes total to all in, just to execute the query. Okay, so that's definitely, like, it took almost, we were able to execute this query in just a little bit more than it took to plan the query using Hive. Okay, but now if we add in the min-max filtering, so again, if we go in that metadata, use those min-maxes, those upper and lower bounds are in the metadata to continue to filter manifest, filter individual data files, that becomes even more performant. Now you're only talking about 412 splits for that same data. So a lot less to scan, a lot faster to scan. And basically it took a little bit longer to plan because you're doing more filtering. But because you took a little bit longer to plan, you saved a lot more time on the total execution. The total execution time, 42 seconds. Okay, so we went from like taking, not only being possible to query a few days worth of data because it would just take so long, to being able to run these queries in like less than a minute on petabytes worth of data. Because you have this nice tiered metadata system that allows you to kind of filter what you need to look at on different levels. So for very specific queries, you can really eliminate, again, what you need to look at as you go along, which really speeds up the planning. So overall, what are the benefits of this design? Like, what makes this, like, why? Like, we see how it works, but what is this really giving us? We can now officially make smaller updates, because if I just want to update one record, well, because of the way the metadata is structured, I can just identify that one file that has that particular record and only update that file. So I just rewrite that file, move on with life. I'm not having to like update the whole partition or scan through all the files in a partition to find where that record is. It's going to be a lot faster, a lot more crisp to make these small granular updates. Okay, and plus you're making changes at the file level. Again, you don't have to make changes at a partition level. You're doing it at the file level because we got all that metadata to track those files. You have snapshot isolation. Okay, and with a snapshot isolation, this has some really cool benefits. Like, one, reads and writes will never interfere with each other. Because if a read comes in, it's always working off the newest committed snapshot. And if there's a writer writing at the same time, they're not touching any of the files that already exist. So that's not going to affect that current snapshot. But when they're done writing any files they need to write, they'll create a new snapshot. But basically, since that snapshot's not committed till they're done, that won't interfere the concurrent read. So basically, readers never have to worry about, like, hey, are there writers? And if you have multiple writers, what's going to happen is you'll use optimistic concurrency writing. So 2 writers, 3 writers, if there's multiple writers, on the onset of planning the query, they're going to like project, like, I think I'm going to be metadata file 5. But if they're done writing everything, if they go back and they realize, hey, there's already a metadata file 5 here, I thought I was going to be 5. Well, then they realize that somebody else has finished writing while they were writing. So what they do is they're going to go back and replan their write, see if they can still reuse the files they've already written, and then make the next, snapshot from there. So essentially what will happen is that the writers will be able to check, like, hey, did someone write while I was writing? And again, since you're never editing the old files, that makes it very practical to do that. So you're not going to have any like overlaps in writing. Worst case scenario, if you had like lots and lots of writers for whatever reason, what would happen is that there is generally, you can set like a reattempt. So you can say, hey, this table only allow there to be like 3 reattempts, for writing. So then what happens if a writer can't successfully write after 3 attempts, that write will fail, but you'll never have like 2 conflicting writes. And so you'll never have to worry about like consumers querying partially incorrect data because the write didn't finish. Faster planning and execution, again, because of things like min-max filtering, because of the partition filtering, and there's other metadata that's being stored in there, and there, like you have like the counts of files in there, the counts of like which files are added. Like there's a lot of metadata in there that can be used by an engine to plan those queries faster, to kind of determine like, hey, do I need to look at this? So as engines, continue to take a look at the data that's in there, these column stats, and for the individual files and manifests, they'll be able to do more and more sophisticated planning. So that's just going to continue to get faster and faster. And on top of it, they're adding even further stats because they're building this like column stats format called I think it's like called Puffin files, and that's going to actually have even more additional metadata in a binary format that engines can then read and do other operations with. So that's just going to continue to get better. Reliable metrics, because instead of having to keep track of those metrics by doing these analyze queries, you're actually updating the data every time you do a write. So you're doing it incrementally, which allows you to have up-to-date stats all the time. Again, you're abstracting the physical. And that way, all your consumers, all they have to do is worry about the logical view. Again, they don't need to worry about how your data is engineered. That's like that hidden partitioning feature we talked about, where basically the consumer doesn't need to know how it's partitioned relative to the timestamp. They just need to query the timestamp field. Like, hey, I want to look for records within these 2 timestamps. And then behind the scenes, that partitioning is going to help that query. The actual end consumer doesn't have to think about that. It's not. They only have to worry about what they're trying to analyze, not how the table is engineered. That stuff is compaction. Now, really, the benefit here is that what's going to happen is that in the Iceberg API, in those libraries that they provide and extensions that they provide for Spark, they have provided tools for running compaction jobs. So if you're streaming data using Iceberg, what's going to happen is that you're generating a lot of snapshots. And this is going to be generally true for all the table formats. Basically, you're creating a whole bunch of files every time data comes in. So you're going to end up with all these small files, which will slow down your queries because you're scanning more files for less data. So you're going to generally want to compact them, take all these small little files with only a few records and turn them into bigger files with more records. So that way, again, that whole file open, file read, file close cycle becomes reduced, speeding up your queries. So there's procedures in the Iceberg API to help you do that. And it's really actually pretty cool because when you run compaction, you could just say, hey, just condense my files, but you can also have them sort the files by like a single column. So that way, if it's a column that you filter by a lot, it'll speed up your queries. And they just added like a week ago, they added Z order sorting. So now you can sort by like multiple columns using that sort of Z order strategy, which can, especially if you're running a lot of queries that you're scanning by multiple dimensions, that can really speed up your queries. So that is cool. Tables can change over time. You can change the schema at any time. You can add columns, remove columns. You can rename columns, change the type of the data types, and so forth. You can reorder columns. You can update the partitioning. And this is the only table format in which you can change the partitioning after the table is created. So in any other table format, you would have to rewrite the table if you want to change the partitioning. So that's really unique to Iceberg. But you can also change like how the table is sorted because there's actually a sort order property. So that way, whenever it writes, it knows to sort the data when it's writing. But bottom line is like it's very flexible, allows you to experiment. Okay, so data engineers can transparently experiment with the table layout. And because you have the snapshots, if you make a mistake, you can always either alter the table again, or you could roll back to a previous snapshot and go back to what the table used to be, which is pretty cool. And that just gets, and if you use something like Nessie as your catalog, that only gets more extreme because now you can do like branches and you get that whole ability to say, hey, you know what, I'm going to create a branch, work with my data, and then I can merge it back in later if I want and isolate your work on data even further, which is really cool. Rich schema evolution support, we already talked about that. Like you can add, drop columns. The thing is that again, it's all the work, all the planning is done with files in your file system, which again could be object storage, could be HDFS, wherever you're storing the data. So what's going to happen is that if I were to run like ingest streaming using like Spark, okay, and I'm just ingesting all this data from the stream through Spark, and then I'm running queries using Dremio, Dremio is going to see the data right away because basically it's going to go in there, regardless of what's going on. It's all pointing, that catalog is pointing to the same metadata file in the same file system, okay, and it's going to then scan that newest metadata file for that newest snapshot and scan the newest data to the table. There's no like lag between that. Same goes for any other engine that reads Iceberg tables. So it makes it where basically anyone operates an Iceberg table, all other engines can see it right away. Because basically all they're doing is just going to that catalog, and that catalog is always going to point to the newest metadata file. So yeah, so that's basically Iceberg in a nutshell. There's a lot more. I have a lot of articles written specifically over that subsurface. So if you go to dremio.com/subsurface, you can put the Apache Iceberg to get specifically the Iceberg stuff. But there, like, we have a bunch of articles we've written in Iceberg and a bunch more that are coming. Some really cool stuff about like handling things like GPDR and more about the object storage piece that I was talking about earlier and more. But you can also go to iceberg.apache.org. You can see the Apache Iceberg blog by going to iceberg.apache.org/blogs. And you can get hands-on by going to iceberg.apache.org/getting-started. Also, reminder, feel free to follow me on Twitter over there at @AMDataLakehouse or add me on LinkedIn. So that way, anytime I put out new content on Apache Iceberg or table formats or data lakehouses in general, since that's what I do. I am here to talk about data lakehouses all day, every day. I'll be posting it there. So at this point, I'll open it up to Q&A if anyone has any questions. They just come off mute. Mhm.
No, I'll definitely start. Thank you so much. That was an excellent talk, and the walkthrough was even better. Like, I really appreciate like when you take the time to really walk through the actual process of how Iceberg, you know, goes through the manifesting process. And that was something that I was a bit naive on myself, was the fact that I didn't realize that the structures really protect you from stuff that Hive and Delta Lake don't really cover in terms of their core architectures. So
Mhm.
that's really refreshing. Plus, I also didn't know about Nessie either. I'd been focused so hard on doing this with AWS integration that I
Mhm.
completely breezed over the documentation part with Nessie was there. So I was like, I really need to check that out now as well. So
Yeah, it's pretty cool. I mean, not like to be that guy, but just like there's a little bit more about Nessie. Is like you basically you can either like host it yourself, so basically you just like run a Nessie server, but also like one of the things we've done at Dremio is we have this service that's currently in preview called Arctic, which is really just like it provides you a Nessie server, so that way you just literally just sign up like you sign up for email, and then you have a catalog for which you can interface with your tables, and actually a UI where you can like create your branches and merge your branches. Is really cool. And in the future there's gonna be some other like services like for ingestion and stuff that'll be added to it, but just for the catalog itself, it's really cool.
and I also noticed conveniently, and Alicia already left, but I was going to note that Dremio conveniently has a name inside the Iceberg documentation. So I thought that was something that was extremely handy. It goes directly to you guys' Apache Iceberg integration site, which is actually really well detailed. And it always speaks to the maturity of a project when the documentation is easy to follow, especially for intermediate and novice engineers. So I really appreciate that aspect as well.
Yeah.
So in terms of like migrations from, let's say I'm currently running Hive and Delta
Mhm.
Lake to do a lot of the heavy lifting that Iceberg can do, obviously much better. What does that migration kind of look like, or where should some team get started if they're
Mhm.
looking to move from Hive to Iceberg?
Got it. Okay. So I'll give the brief and low of it. For extra details, I do actually have two articles on this specific subject, which are at the Subsurface website. So I do specifically on Hive going to Iceberg. But when it comes to migration, you have a couple different options. It just depends on, do you want to restate the data or do you not want to restate the data? So if you don't want to have to like rewrite all the data files, what you can do is that there's actually a procedure in the Spark Iceberg libraries that called migrate. And what migrate will do is it'll actually take your catalog, take your Hive table, and it will write out the metadata around the files that already exist. So you're not writing any new data files. They'll just exist wherever they've existed up till now, but you'll have metadata files that refer to those files as part of the newest snapshot. And you'll have this new table in your Iceberg catalog. The only catch is that it does sort of like destroy the Hive table, so the Hive table no longer exists afterwards, but all those files are now an Iceberg table. So generally you want to run, before you actually do that, there's another procedure called snapshot. And what snapshot will do is it'll create a temporary Iceberg table. So that way you keep the Hive table intact, and then you can see what the result would look like before you commit and do the full migration. But basically, that way you're not writing any new files. So it's like the quickest way to convert. The other way you could do it is you could just do a CTAS, create table as statement, and basically then you're rewriting the table. But the benefit of doing that is you could actually change the partitioning and have put partitioning clauses and other clauses to restructure the table at that point. So that way, if there was like a field you wanted to kind of rename or anything like that, you could just do that as part of your CTAS statement, and now you have the table with all those changes nicely rewritten going forward. So it just depends on sort of like, were there things you wanted to change? Then the CTAS is probably the route to go. If you're happy with all the data as it is and you just want to use those same files and just kind of move forward with life, the migrate will be the quickest way. And if you're migrating from, like, let's say Delta Lake tables, Apple, I think it was people from Apple, they just put a pull request to add a utility that'll convert Delta Lake tables to Iceberg. That's not like, hasn't been merged in yet, but that's on the way. And then another migration issue that comes up is, what if you have because base is the catalog. So what happens if you're using Iceberg today and you use like a Hive Metastore catalog, and that's been working for you, but eventually let's say you want to move over to Nessie. How would you do that? Up till now, basically you had to like do a CTAS and you would lose all your snapshot history when you do that. But now all the catalogs, they have this method called register table. So what would happen is that, hey, I have right now it's in the Hive catalog, but in my physical file system, there's all those metadata.json files. So the newest one, let's say it's v20. So what I would do is I would go to my Nessie catalog, say register table, and then just give it the path to that newest metadata.json file, and then it'll register a new table with Nessie pointing to that new metadata.json, and then it'll just work from there going forward. So now you can retain all that snapshot history when you're going between different Iceberg catalogs. So there's ways to migrate catalogs, there's ways to migrate from Hive, and soon there should be a very clear path for migrating from Delta Lake.
No, that's actually fantastic, man. And like I said, it's good to know, especially since one of our customers, they're just now looking to get a data lake set up. So it's like, for us, it's kind of a no-brainer to start with Iceberg from the get. That way there's, minimal onloading, and they already have, the only thing they have to worry about is, appropriately and rapidly populating their Elastic store with all the files. So an Iceberg, and the Delta Lake will take care of the rest, or Data Lake will take care of the rest.
Yeah, it's pretty great. Like, it's pretty flexible in the sense that like you can always like dip your toes in Iceberg and then just continue like switching tables over as you need. Because let's say you're already using Hive Metastore, you could use the Hive Metastore as your Apache Iceberg catalog, and then so that way everything just kind of coexists, and then just switch tables over as you feel comfortable. So that way it's not like an all or nothing proposition, which is nice.
Yeah, excellent. Well, I think that's pretty much all I had, and I don't think